everybody. Thank you for joining us today. Special thanks really to those who were here last week for the introduction of the solar system track and still come back for more. So today my talk is about advanced tools, especially applicable for lunar analytics in support of mission planning, situation awareness, and also research using the Moontrack portal. For those who weren't here last week, Solar System Track is a GIS platform of web's online portals for visualization and analysis of large amount of data in 2D and in 3D. Just simply go to track.nasa.gov and you will find 7 portals publicly available. Among them, I would just have to say that Moontrack is the most sophisticated and also well-invested one. It has close to 10,000 data products and also has the longest list of advanced capability, which are being used by lunar mission planners, scientists around the world. So when you go to Moontrack using the URL track.nasa.gov/moon or just through the Solar System Track home site, on the menu you'll find a set of publicly available tools. It includes basic tools to measure distance, generate elevation or sun angle profiles, or generate STL or OBJ file for your 3D printer, and also fly over in virtual reality. And as I have shown last week, data from different instruments can be integrated together by just stacking and blending them together and then easily share with others. Today, I would focus on introducing the set of advanced analytic tools, specially designed and targeted for exploration and science. These advanced tools are limited for use by registered user only, partly because they are not appropriate for the public, but most importantly, they require enormous amount of CPU power, memory, and also storage to process the large amount of data. Since the system is built on a scalable backend infrastructure that leverages a hybrid computing platform, including the Amazon cloud services and storage, it could actually, cost quite a bit for the project to support the use of these tools. You can click on the sign in to log in to access this advanced tool. If you don't have an account, feel free to just register. We would just ask that you share with us your use cases and why you would like to use the tools. Oops, now I can not move forward for some reason. So many of the lunar products that we have available on Moontrack are huge in size. For example, the size of Kaguya Orthophoto Mosaic is about 500 gigabytes. You would probably only want to create a subset of such large data set for your research. The subsetting tool, it comes in handy for you to select specific area of interest that is smaller representative area or focused region to work with and really make it much more manageable for processing and manipulations on your own computing platform. So the result would be download and then open for viewing automatically. The rendering speed obviously will vary depending on the size of the area and bandwidth and your machines as well. So this tool is written in Java and also uses GDAR library. I touched on this tool last week. Crater detection is another advanced tool on Moontrack. It is an image-based tool that finds craters on LRO NAC images. It uses edge and lighting condition detection techniques along with a recognition method via machine learning convolutional neural network to find all the crater candidates. You select specific area of your interest, and then any of those available NAC images in that area, the outputs of the crater detection will include a heat map based on crater density, an image with craters labeled by all the bounding boxes over those detected craters, and also a text file that lists lat-long location, estimated diameter and depth of the crater, and also the confidence value for each of those craters found. The detection portion of this tool is written in Java, and it uses the OpenCV for image processing routines. And the recognition portion is written GNU octave. So rock detection is another image-based advanced tool. It uses classic computer vision techniques to identify rocks on LRO NAC images again. The techniques include gradient computation, image sharpening and contrasting, and threshold applications, and analysis to find as many rock candidates as possible. You again select a specific area of your choice and then any of the available NAC images in that area. And the outputs of the rock detection would include an abundance chart based on the rock density, an image with rocks labeled by bounding boxes, and then a text file that shows the rock coordinates in the image pixel space. This tool is written entirely in Python. Again, it uses the OpenCV and also SciPy and NumPy for image processing and analysis. Slope analysis is an elevation-based tool. It estimates gradients and slope data on a given digital elevation map. It uses different convolutional filters and algorithms to compute gradient estimate of each point in the digital terrain model and by sampling the neighboring points around it. You select specific area of interest to do this analysis and the available digital elevation map in that area. And the output of the slope analysis will include a topographic map showing contour lines and also a map in GeoTIFF format that contains the gradient values. The tool is written in Python. Surface lighting. It models the direct and reflected scattered light and estimates the amount of light across the surface available as a function of time. It uses ray tracing technique and also takes into consideration of orientations of the sun, the moon, and also the earth, and also the effective albedo of the earth as well as the lunar topography. You select area of interest, the start and end time, along with the time intervals for the modeling. For each of the time increment, the tool would output an gradients plot of value which shows watts per square meter, a text file that lists the lat long and the associated radians value, and also a simulated GeoTIFF. When combine all the GeoTIFFs, that would give you this animated simulation. The lighting analysis is particularly useful for solar panel design, for example, and path traversal, in which how much sunlight is available is very important. This tool is written in C++. Surface electrostatic potential calculates ionization potential due to solar wind striking the lunar surface over time. It uses a surface plasma model that have the algorithm developed by Dr. Bill Farrell. He's a plasma physicist at the Goddard Space Flight Center. The algorithm includes comparison of the surface ion flux and also the solar wind ion flux. So users select a special area for this analysis. The output of the tool would include a distribution map, a plot of the electrostatic potential values relative to the solar wind, and also a plot showing the ratio of the surface ion flux to the solar wind ion flux. This tool is written in IDL. It is particularly useful for understanding the electrical environment within those permanently shadowed lunar craters. Especially that we work on this pipeline is to support the lunar exploration and science. This is a Mosaic pipeline that provides a turnkey and automated workflows that create high resolution stereo elevation and also mosaics from the orbital imaging. This pipeline that automates the stereo pairing selection based on overlap regions, sun angles, spacecraft geometry for users specified regions, and then the workflows would process the data ingestion, do the stereo reconstructions, alignment, and also removal of outlier points and also distortion. For the ease of use in conjunction with the DEM Mosaic, the pipeline also produces an associated ortho mosaic that is color balanced. This pipeline is written in Python. It uses a slew of free and open source programs, including USGS, ISIS, and AIM stereo pipeline, GDALS, etc. A few of the examples outputs are illustrated here. I am actually really happy to announce that just last week, Caltech has approved the open source of this pipeline. We are currently determining which open platform to push it out. It would definitely welcome any contribution to the production code base. If you're interested, feel free to contact me. There are other tools being developed by us that will be applicable for research. They will include a calculator that calculates the line of sight between two objects, a feature detector that will classify and detect a given type of features such as lunar rail, rock craters, lunar peaks, etc. In addition, to the rock and crater detector we already have. So using those different tools, we can actually benchmark the output of those analysis. A path to rebuilding is that will find the optimal path between 2 points on the surface of the moon that is based on a slope analysis. We are also actively working with our international partners. The current collaboration with the Italy's Frascati National Labs produced a beta version of the Lunar Reflector calculator. And our current work with Max Planck Institute leads to a rockfall detector that finds rockfall in RRO images. So going a little bit detail about the line of sight tool. The purpose of this calculator is really to identify the visibility between two objects as a function of time. It uses planetary geometry and in some cases depending on the digital elevation maps. For example, you can calculate the line of sight between a rover on the surface of the moon and LRO, or between a point on Earth and LRO, or between 2 points on the moon and the Earth, or even 2 points on the moon, taking into consideration of topography. So currently we have a prototype that is accessible only through APIs only, and more work will need to be done, and eventually this calculator will be available on Moontrack. The Lunar Laser Reflector tool is intended to support planning for future retroreflectors and ranging deployment, and also reflector research, as well as lunar interior and precision tests of general relativity. This is being used to predict relative geometries between the Earth laser stations, the reflectors, the LRO, other orbiters, and to find images taken by the LRO showing reflections on the sun or laser of the reflectors. The output of the tools include time intervals for viewing a solar gleam from the reflector, as seen from the LRO using a map view showing where they are positioned. And also LRO net images that are available in PDFs that have the reflectors in view, or images available in the PDFs that have the solar glint of the reflectors. As I mentioned, the beta version is already available on Moontrack. This tool, I think, is written in Python and uses Spice kernels. The Rockfall tool is another image-based tool. It uses the machine learning convolutional neural network to find rockfalls in net images. Finding where the rockfalls are on the moon is useful to study seismic activities and erosional state of lunar surface. Recently, a global rockfall map was created actually using this tool. When the tool is integrated with Moontrack, you can then select an area of interest. The output will include a rockfall heat map showing the distribution and density of the rock faults, and also a text file describing the map, the long estimated size of each rockfall. So in summary, Moontrack's advanced tools are being used by mission and researchers already today to explore and study the moon. Our goal is to make it easy for lunar mission planners and scientists to find and analyze the large amount of data returned from a variety of the lunar missions. So we are committed to continue enhancing our toolkit, and we love to get your feedback to help make Moontrack more useful. And we certainly welcome any collaboration opportunities, whether to create new advanced tools or to host data sets of tools that you might want to share with the lunar community to advance lunar science and explorations. So in closing, I'd like to thank you all for your time today, and also thank our sponsors and partners that we're working with. So with that, I will take any question you might have.